In this paper, we propose a method for surface reconstruction in NLOS scenes. Non-line of sight imaging is to reconstruct the invisible scene from the sensor and light source. In the NLOS setup, the sensor only sees the visible wall. The typical input of the NLOS imaging is the indirect light captured by a time-resolved sensor, such as a single photon avalanche diode, SPAT. The SPAT observes photon count at each arrival time, which we call a transient histogram. The time resolution is from nanosecond to picosecond. We summarize scene representation for NLOS imaging in the previous studies. The traditional NLOS imaging, LCT, estimates volumetric density at each voxel grid. DLCT extended to LCT with surface normals for NLOS surface reconstruction. However, these methods are limited due to their discretized scene representation. Recently, NETF is proposed for NLOS imaging with a continuous neural radiant field. However, this method does not model an object surface explicitly. Our method extends NETF to output an implicit surface with a neural field for NLOS surface reconstruction. We show the result of surface reconstruction on synthetic data. Because NETF uses radiant field without explicit geometric representation, the reconstructed surface contains large errors. On the other hand, our method with implicit surface can reconstruct the smooth surfaces. We also show the reconstructed surface on the real data captured by a SPAT. The reconstructed surface with DLCT contains artifacts due to the discretized voxel representation. On the other hand, our method with a neural implicit surface can reconstruct the smooth surfaces while preserving the fine details. This is the overview of the proposed method. We first sample 3D points on the sphere centered at the point on the wall. The radius of the sphere corresponds to the time beam of the histogram. The sampled point is then passed through a MLP to estimate signed distance and reflectance. The signed distance is converted to density for volume rendering. We use the efficient conversion proposed in style SDF. By taking the sum of the reflected components on the sphere, we can render the value of the histogram, which is then used for computing a training loss. In practical scenes, background effects, such as the reflected light from objects other than the target, are not negligible. We propose a background network implemented by shallow MLP to render a background component during training. Our approach correctly divides measure transient into an object and a background component, and enabled the SDF network to run correct SDF. We found that limited observation in the NLOS setup led to incorrect SDF. To avoid this, we propose two loss functions for learning SDF in the NLOS setup. One is self-supervised zero-level set learning to learn a correct zero-level set. The other is a constraint for volume rendered weights for suppressing effect from non-zero signed distance points. We also introduce an SDF constraint based on the geometry of the first returning photon. From the traveling distances of the first returning photons, we can apply space carving to the NLOS scenes to obtain the free space and rough shape. The signed distance of the rough shape forms the lower bound of the true signed distance, and we can leverage this lower bound as the additional training loss. We show reconstructed depth maps from zero-level sets after training, with and without the proposed loss function. We demonstrate the effectiveness of the proposed loss functions. In summary, we propose a method for surface reconstruction in NLOS scenes. Our representation with neural implicit surface enabled high-quality surface reconstruction in NLOS scenes.